Our next speaker is basically our newly appointed head of department, Professor Guillermo Narsilio. He's a global recognized leader in the energy geotechnics and infrastructure engineering with his team. He has led pioneering research in shallow geothermal system. He's co-founder of 4EE, a boutique engineering consulting firm spinning out of the University of Melbourne and specialized on energy geostructure and ground source heat pump systems. Professor Narsilio has secured over $10 million in research funding and has established high impact industry partnership. He served as a chair of ISSMGE technical committee, it's a very long name, on energy geotechnics, and is the former ARC future fellow and of the Australian Research Council of the expert member. So please join me to welcome Guillermo.
So my talk today is perhaps coming smaller in scale in a way of what we have here so far, and it's about ground source heat pump systems and the potential use in infrastructure, projects, buildings, and particularly the use of foundations as thermal energy sources, that is. And the work that I'm presenting today is not just on my own. There are many people, many very bright PhD students and postdocs that will help along the way. Probably I don't need to tell this audience that some of the key challenges of the 21st century is around managing resources and moving towards cleaner sources of energy. And when it comes to heating and cooling buildings, these account for more than 50% of the energy use and around 25% of the carbon emissions. That is 10 gigatons, 25-30% of the total emissions worldwide. Now, there are alternative renewable sources, technologies, and we have heard of deep geothermal systems in a way, power generation typically, and more shallow ground source heat pump systems. I'm going to focus today on the shallow or the ground source heat pump systems. So the analysts come there. So how does a system work in line terms? What we see here is, I don't know what the point is. Okay, what we see here in green is a ground source heat pump, and that is connected to, in this case, a closed loop. What we have seen so far has been open loops. This closed loop is formed by plastic pipes, ATP, high-density polyethylene pipes buried into the ground to form a ground heat exchanger. We circulate water through these pipes, water or a water antifreeze solution, so that, let's say in summer, we inject water at, say, 30 degrees. The ground is a very stable temperature throughout the year. The upper 100 meters of the earth around 19, 18 degrees. In the case of Melbourne, is the mean, typically the mean temperature throughout the year of the particular location. And because the water that we inject is at 30 degrees, say, the ground is at 20, the ground acts as a sink of heat. We're rejecting heat to the ground. Now that water, that fluid comes back to the surface, to the green box over there, maybe 3-5 degrees lower temperature. So that differential in temperature is used by the heat pump to then provide either cooling to the building on top or heating if we do a reverse cycle. This is not too different from what we have a split system at home that is reversible. The big difference is that in summertime, your split system is rejecting heat to the air, which is already hot. So you need to use a lot of energy to move that sort of thermal differential. And in winter, we do the opposite. We take heat from the ground, but from a much higher source of thermal energy than the air would be. A reversible air source heat pumps take heat or thermal energy from the air that in winter is much cooler than the ground is. So inherently, the amount of energy or work that we need to put into the heat pumps when we use ground heat exchangers is on average throughout the year lower typically than an air source heat pump. And this is where the savings come from. Now, how do we materialize these ground heat exchangers? Typically through traditional boreholes going up to 150 meters into the ground, 4 or 5 inches in diameter, 10 centimeters in diameter, or in more horizontal trenches that goes up to 1.5 meters into the ground. This is how a horizontal, shallower system looks like before backfilling, and this is heating and cooling, mostly heating really, a chicken farm in New South Wales. So these are the horizontal loops made of this plastic I mentioned before, HDPE, and this is before backfilling. So then we cover with 1 meter of dirt and the heat exchange occurs. How does a ground source heat pump plant looks like? This is an example in Picard in Narrowwarren, so maybe 40 kilometers southeast of where we're now. And one of the heat pumps are there is a battery of them, a couple of them, and all five being connected to the ground and then also servicing the building. Now, because almost everything is underground, you cannot see it. In this particular building, they have a see-through floor, so you can see those ground heat exchangers, those pipes there. Okay. There are some advantages to this technology, and sustainable and renewable source of energy that is available 24/7. It provides significant carbon footprint reduction because it's more efficient. We do need to run the heat pumps and circulation pump for the water using electricity, but at a much lower rate than the alternatives typically. This established technology, we have more than 7 million of these installations worldwide. HVAC and heat pump technologies is well established, and it can be used in conjunction with more traditional systems. It can be used anywhere. So there is no geological restrictions. And there is also, as our American colleagues just said, visual and noise reduction, because we can put this into a basement. There's no need to be external. But this is not a magic bullet. We also have some disadvantages attached to it. It's having largely overlooked in the country and in some other places, but this is changing. Few people have heard of them. Now I have at least 40 more that are heard of it now. And we have typically high capital costs or high upfront costs. But this may go down as industry matures and we have more competition if carbon taxes are introduced or subsidies are introduced as well, like we did with solar PV to get the technology out there. Now, I did mention that one of the limitations is the high capital cost associated primarily with the drilling. 50% of the capital cost typically come from drilling this 100-meter borehole. So what we thought is maybe we can not use that purposely built borehole and instead embed those pipes into the building foundations that we need to drill for anyways. So safe, there is no additional excavation cost. We did some estimation back in 2019. The saving is around 30% of the installation cost because we still need to have labor involved. Some material is really cheap in this country, but we still need to coordinate with the program of the building. And that's perhaps the one that made the saving not to be 50%, but a bit less. So now we have other options for ground heat exchangers, and we call that energy geostructures, energy foundations. So this includes piles, retaining walls, tunnel linings, roads, underground utilities, and even when we are closing mines. Any structure that is in contact with the ground can be converted into a ground heat exchanger to save capital costs. And this is a nice picture from one company elsewhere, where we see cartoon, if you wish, of energy tunnels or energy walls or energy piles. These are the pipes that we embed into these structures. Now, geostructures are very abundant in transport infrastructure projects and also in buildings, particularly tall buildings where we do need the foundations to them. And I just put some examples there. How do these geostructures or energy geostructure looks like? This is a pile or energy pile before we put the cage into the ground. It's a bit hard to see here, but we do have also retaining walls, and this is the Melbourne Metro project, the State Library station. So we can embed pipes into the retaining wall as well to act as a heat exchanger, the lining of the tunnel, and even roads. So these are three of them are projects that we work on with the colleagues in our group, and there are some lessons learned on the papers that I'm listing there. I'm not sure whether I have the time, but I'm going to just reiterate.
Geothermal energy is using the thermal energy that is stored in the ground and with the help of a heat pump, providing heating and cooling to the buildings that are on top of the ground. At the State Library Station, we have installed a shallow geothermal system by embedding some plastic pipe into the retaining walls of one of the shafts that are being built. In this way, we can harness thermal energy from the ground and from this wall to provide heating and cooling to both the station as well as surrounding buildings. So in winter, say the air temperature is around 10 degrees, but our ground is at 18 degrees, so it's much warmer. What we do, we inject water to pipes embedded into retaining walls, and that water picks up this thermal energy from the ground and comes up much warmer on the surface. Then the heat pump boosts it to provide heating to the buildings. In summer, the opposite happens. We take heat from the ground and imagine that you have the air temperature of around 30 degrees. The ground is still at 18 degrees, so it's much cooler. So what we do, we dump this heat from the buildings into the ground so that we can provide air conditioning to the buildings on the surface.
All right, now you have that
Geothermal energy is
with subtitles, so if you are not used to my accent. We can embed these pipes into other type of structures. So you're a geotech engineer like myself, and this is another type of pile, foundation screw piles. This is the project in PyCAC in Arreglar during the construction, actually. Yeah. Melbourne Connect, the building 100 meters away, we have also, as a little trial, show that we can thermally activate slabs. And if you look closely, you can see some of the pipes embedded in this 1 meter thick slab in that building. And Fisherman Bend, we did try also what we call driven pipe. This is pipes that we drive into the ground because that's quite soft. And we tried many different configurations. The difference here being those pipes sticking out, which are the ones that we use to circulate water and exchange heat with the ground there. Now, in our earlier papers, technical papers and talks, we have said, ground source heat pump systems work well when we have a balanced thermal load. We need to provide as much heating and cooling in the building because basically you are rejecting heat to the ground in one season, warming up the ground if you wish, and then you take that heat back from the ground in the winter time, the other season. So when you have a balanced thermal load, we use the ground as almost a thermal battery. And that's great for geothermal that minimize the size of the ground heat exchangers. If you do have an unbalanced thermal load, and the state library and the stations here, Parkville Station is requiring a lot of cooling, air conditioning, that will mean that you are rejecting heat to the ground all the time. And eventually you may overheat the ground. And that's true in the absence of groundwater flow. And so you can see here, this is the shaft station of this is the station box that we model over time. That's 40 meters in depth. And you are accumulating heat over here. This is 30-year simulation. And it becomes not feasible. After 10 years, in this case, the ground you're heating up so much that it becomes less efficient than alternative. Not good. But if there is groundwater flow, that's great because now all that heat that we're rejecting with the ground is being flushed away. So even with a very unbalanced load, if we do have some groundwater flow, not only thermal conductivity of the ground is higher because it's a wet sort of ground, but also you have this flushing away, this convective heat taking it out. So that's good news. How do we go about the ground heat exchanger design? We have generated throughout the work at Melbourne Uni with the group charts for design for piles and retaining walls. But we also have developed this very computationally expensive web application software. It runs detailed finite element models in the cloud. So in your browser, you can enter your geometry, you click run, solve, few hours, few days later, after we run this in supercomputers in the cloud, you get the results. And now piggybacking on what we said before about AI, we have trained some maybe 10 years ago. We were one of the first in training a machine learning thing, so in AI to replace that process. So we run a number of detailed finite element models, and we use the result for many different conditions to train a AI model so we can get results in a fraction of the time. So we went from hours or days to just seconds and minutes in that case. But it was for specific ground heat exchanger piles in this case of many different configurations. But there is also an app for that. So for pre-design, not for design, pre-design, we have generated this app called Geothermal app that are available in both the Apple Store and Google Play if you want to have a play with it as well. So ground source heat pump systems and particular energy geostructure, we have seen that are technically feasible in the computer with simulations and in real life with demonstrations and some becoming full scale, like the PyCAP project. Even using retaining walls and slabs that have contact with the ground only on one side. The other side is either your parking or your station, your basement. Even those, or a slab, which is the same but horizontally placed, can perform well under the right conditions and design. The balance of the thermal load distribution is critical to the performance of the system and to the cost in a way. But this is not so much important if there is groundwater movement that can flush away all that excess heat in the ground. Now, I think that this has been mentioned by all of the speakers so far. Collaboration of different buildings or companies or entities is necessary to achieve a balanced thermal load in a case, or to achieve the construction of these systems. HVAC systems are typically constructed or built at the end of the construction of a building or the infrastructure project, with some provisions at the beginning. With this ground source heat pump system, because of the ground heat exchangers, we need to be in at the very beginning of the construction, not only on design, but also the construction. We need to wait until the superstructure is mostly built to then come back and finish up, hook up the pipes to the plant, basically. And that's a bit different. There are barriers to implementation. Regulatory was mentioned before. That's particularly for deeper tapping into geothermal sources. But in general, these are overcome through R&D, and we have done this for more than 15 years now with RMPs as well, and full-scale demonstrations. We know that first mover will be winners. When we were doing the Melbourne Connect building, Melbourne Connect has around 100 piles and a lot of works. We're only given 20 of them to try. So a small percentage. There are no economies of scale there. The building contractor Lend-Lease was on board, but skeptical. And it was great to hear that in the end they said, oh, it wasn't rocket science, it was easy. There were no delays to the program. That was the main concern. There were no leaks into the building that we could not detect and so on. So with that, perhaps I thank you for your attention now, and I want to acknowledge all the work that has been done by the members of our research group, and some of them are here today. So Marin's over there, also some involvement with Graham and Besser and Rachel's work. For R&D, that's my contact details. For commercial designs, we have a different arm. Sometimes industry government prefer to work with industry or consultants as opposed to universities. It's not only the pricing different, but maybe a perception. So my contact details are there. Thank you.